glad I rewrote that.
Yes, you have my permission. Okay. I'm going to do a couple things, and one of which is on just the thought process that takes place when you actually acquire data and then going into the error propagation analysis stuff. Okay. The data that you took was resistance versus temperature, right? And a lot of you went out of your way to graph something really weird. It's fine, but if that's what you measured, that should be your first pass at actually graphing anything. Okay? And this is what I did when I did the analysis that I'm going to show you. Okay? Because these are the data that were taken. I try and minimize the number of steps I have to do. And yes, you could do delta R over R and delta T. But I have to calculate the error for that. I have to calculate the error for that. When I already have the error associated with R and T, I already have them as part of my data. So I don't have to do anything differently. And when graphed, and I'm picking on the inductor because the inductor was so pretty. Okay? Almost everybody's inductor turned out pretty. So took a data set from somebody in the class and I graphed it. It was linear. This is at 0C. So I'm going to define R0 as the temperature of 0. Okay, so instead of R0 being room temperature, I'm going to go ahead and use temperature of 0 to be my set value. Okay. So I went ahead and did the curve fit, and the curve fit gave me okay. So that's what the curve fit gave me, but I also have at that time, I know that R is related to the resistance at, in my case, 0C, 1 plus alpha, the change in temperature, T minus 0C. So now this works out pretty nicely because just doing a little bit of rearranging, I now know what my slope and intercept actually are. Okay. So my R0 is the 106.96 plus or minus 0.13 ohms. So not only do I know what R0 is, I also know what my uncertainty is. My slope is going to be R0 times alpha. So now I only have to do one error propagation calculation, whereas if you had done the delta R over R delta T, you would have had to do two. It's not saying it always works out that way, but I can now find this as the slope divided by R0, okay, and I'm going to find the value for that. Okay. So now I'm going to go ahead and get the uncertainty in alpha using the general form. So delta alpha is going to be the partial of alpha with respect to the slope my uncertainty in slope, all squared. Okay. Partial of alpha with respect to R0, delta R0, everything squared, add. Okay? So, the partial of alpha with respect to the slope, you tell me. Okay, it's just 1 over R naught. Okay, the partial of alpha with respect to R naught. Over R naught squared. There's a minus sign, which really doesn't matter in the grand scheme of things because we're going to be squaring it. Okay. And you have the uncertainty of the slope. That's our 0.0022 ohms over degrees Celsius. We have our value for R naught, our 106.96. We have our slope value, our 0.4625 degrees Celsius. Our uncertainty in R naught, our 0.13 ohms. We have R naught already. We've already said that. So, do I need to substitute this in? Can you just believe me if I tell you what it ends up being?
Yeah.
All right, so delta alpha, and I think that is okay. So we now have our full value for alpha. Okay. I like to call, just so that we can distinguish the uncertainties, I like to call this the result uncertainty for alpha. Because how did I get it? I got it by analyzing the results somehow. It came not directly from the graph, it came through information about the graph and a calculation. But it's still heavily dependent on the results. Okay? So, when you're reporting anything in your paper, this is what you're going to be talking about. Okay? Because this is what you obtained from your analysis. Okay? This should be described somewhere. And then here's, and this part saying that, where this value came from needs to go into the appendix. Okay? So what you would do is saying using the general form and applying it to, like, so part of your data analysis would be saying this is the curve fit equation. Alpha is obtained through using the slope dividing by R naught, making these connections somewhere. Okay. This value is obtained. This uncertainty was obtained in the appendix following, and then the appendix would be saying using the general form, applying it to equation 15. Okay. You obtain this relation here. You don't need to put this step down. You obtain this, substituting the values from table 6 for the uncertainty for slope or whatever, you obtain that. Okay? Because I'm assuming that table 6 had all the curve fit equations in there. So you're referencing how this is obtained, but then in the process of obtaining it, you're referencing where where the information was. How are we doing? Any questions? All right.
So you're suggesting that we should, the equations that we get from graphical analysis, we should put it in a table?
Especially for like the resistivity lab, how many? You had what, 4 things? Some people had 6, because they did like 2 inductors, 2 resistors, and then the diode and a piece of metal. So that would be a good consolidation of all the information. Yeah.
As well as putting them on their respective graphs.
Yeah, I would put it also on the graph as well. Okay. So this is what you would need to do in terms of the error propagation for getting your results. Okay? And this is where people stop. And there's a lot more to error propagation for the entire activity that people miss, because I'm going to leave, no, I'll write it again if I need to. So now, what you want to do is try and think in terms of why is your value, is it as accurate as it could be? I mean, what are the issues with the value that you obtained? I didn't even do a comparison yet. Okay? This particular value ended up being about 10% off. All I'm discussing here is the factors associated with error propagation. So, and what I'm going to try and do is get a handle on how much uncertainty in an answer can be attributable just due to the fact that you're taking measurements with equipment that have limitations. Okay? So, this is where you're doing what I would call traditional error propagation. Okay? And why it becomes so important. So if you take the equation, so take the original equation and rewrite it in terms of information that we have, okay? So you would have R minus R naught over R naught. I'm just writing it this way because when I start doing my derivatives, it makes it a little bit easier for me. So from measurement, you actually had a starting resistance, and you had, because there was no value in this table that was actually at 0. Okay. But there was an initial temperature of 22.3 plus or minus 1.1 degrees Celsius. There was another temperature. So I took it over the entire range of values that were reported. Okay. So all of these values were measured. T0, R, R0. And alpha depends upon all 4 of these factors. So I can get an uncertainty in alpha based upon every one of those factors. And so and I'm writing this out to emphasize that this is There's a lot of steps, okay, but it has to be done. Because you have to do it at least once to be able to get a sense of what I'm calling the measurement uncertainty. Okay. And it's pretty mindless at this point because you just, I have 4 things, I have 4 terms. Okay? All right. So, which one do you want to tackle first? Okay. So, there's the equation that you need to take the derivative of. And for this problem, these are simple derivatives. They're just tedious. Oh, don't forget this. So it's 1 over R naught, but then this is all kind of carried along as baggage. So this has got to be 1 over R naught, T minus T naught. Okay? Next term? We're just going to go in order. Okay? What do we have for this? Voice in the back, go ahead.
Minus 1 over R naught squared times T, or with T minus T naught on the bottom.
You ever see that? You sure? This can be rewritten as R over R naught minus R naught over R naught, which is 1. So, dimensionally, something's wrong. There's an R on top. And so these are simple derivatives, and these are the kind of mistakes everybody makes. Okay? Everybody see how we got it? Okay. If not, wait until everybody leaves and then you can sneak in and go over it.
I'm glad it got me on camera making a mistake.
Yeah, but you're hiding back there. You're hiding back there, so nobody can see your face. They just have to, interpret your voice. Scott Thomas. Oh, Dr. Scott Thomas. That's okay. I was doing, given a result, and then I was putting it in microseconds, and they moved the decimal place the wrong way. That was right.
Oh.
Yeah. Okay, so here we go. Derivative time, come on. Audience participation. No.
Negative 1 over T squared.
No, more than that. You got to treat that whole thing as one big entity first. Okay? So it's going to have to be, well, this is just coming along for the ride. This has got to just stay there. It's not doing anything. But this has got to be 1 over T minus T naught squared. Oh, there's a minus sign in there. And then I take the derivative of the inside, which is just going to be 1. Okay? You good? Okay. Making sure I'm getting the same thing here. Okay, and the last but not least, T naught.
About the same.
It's about the same. Okay, we're going to have the T minus T naught squared in the bottom. We have the minus sign from taking the derivative of 1 over something, and then we get a minus sign from this, which becomes plus. But again, it's no biggie because of the fact that we're going to be squaring everything. So, but it is important to make sure you know how to do your derivatives. Okay? So, in looking at this, I then recognized that there was an R naught, T minus T naught in all the terms, that when I substitute everything back up in here, becomes squared. So I can factor them out, take the square root of it, and then I did just a little bit of algebra to clean this up. Okay. How we doing? Thanks, Matt. Any questions about, just kind of like the math part? And Matt will agree with me, so will David. It's just tedious. It's a pain in the butt. Okay? All right. How are we doing? Give me a chance to write it down. Well, we have all our measurement values, and we have all our measurement uncertainties. Now you get to substitute everything in. And I broke it down into each term. I didn't complete the math because I want to showcase what happens next. Okay? So, substituting it, not plugging when you're writing your papers. Plugging, you plug stuff in. Not professional. And I'm not truncating everything yet because I don't know where it's going. Alright, so now I'm just going to look at each of these items term by term. Okay? And what they calculate out to be. Okay? So this ends up being 2.25, and again, I pulled all the units out. You're in front. The second term is 2.379. Third term, 0.3454 plus 0.2473. Okay? All right. The reason I like to do this is because now I can start identifying any factor or factors that play a role. So it came as a small surprise to me that when I'd be calculating the uncertainty for the X-Tech thermometers, you had to take 0.3% of your reading and add 1 degree, which I thought was, wow, that's going to really screw up things. But the issue is that even though it's, in my mind, a fairly large uncertainty, everything you're measuring is with regards to T minus T0. And this is about 70 degrees, so it's number 70. Even though the process for getting this, like the fractional uncertainty of this to this, is smaller than the fractional uncertainty of this to this, when you look at the difference of R minus R naught, that's only a resistance of about 33 ohms. So these individual uncertainties compared to 33 versus this compared to about 70, the temperature becomes less of a factor than I thought it would be. So I can see right here that if you could get better resistance measurements, which could be due to taking multiple measurements, redoing the same trial, getting average values for the resistance, anything along this line, you could improve that. Okay.
Can we go term by term?
You can go term by term. These aren't that different, though. If this were like 23.79, then that would tell me that I would want to focus heavily on this term. Okay? But you can see that the two resistance terms are not quite, but about a factor of 10 higher than the temperature terms. So in that case, I would want to try and get a better ohmmeter or DMN. Okay? So that's one of the benefits of doing all of this work. Because now, when you're sitting there going, well, what would I want to improve? And this is only going to focus on the actual measurement process. It won't take care of any systematic errors that also might be inherent in the experiment. You know, the quality of the device itself, you know, was it really pure copper? Were there issues with other factors associated with the experiment? No. But this will take, you know, say, okay, if I want to improve this part, what would I need to do? Okay? And I have an example to kind of say, like, how can you quantify that? That quantification is not required for 2210, but you need to be able to do it for 4210. Okay? All right, so in calculating everything, the uncertainty of this, okay? So this is the uncertainty, so this is your, and again, I'm going to call this the measurement uncertainty. This is what you could attribute due just to the measurement process. Devices that you used. Okay? So now you've got the uncertainty from your measurements Okay? So now we can see that the uncertainty in the measurements is about 30 times greater than the uncertainty in your results. Okay? So if when you are discussing, let's say that alpha plus or minus the results uncertainty gave you within the range of the accepted value. Now you can talk about how, you know, this is, any errors are probably due to measurement errors, and they're not overwhelming because they kind of got washed out by all the data that you took. So you would want to focus your error analysis most likely on measurement techniques to get things even better. So that's assuming your value is within accepted range. What if your value is not within accepted range? The alpha that we found was about 10% off for copper. Okay? So, I'd have a hard time convincing somebody that it was all measurement error since this is so small. But I might have a better case saying there are other issues associated with the experiment, some systematic errors that may be attributable to why it's 10% off. Okay, the purity of the material. Unknown resistance values that may be in the fluid that you're using. Resistance values for the leads that you're using. The alpha that you obtain from this is too high. So then you would have to be able to argue, would those resistance values, say of the water, say you use tap water accidentally instead of distilled water, and the leads may have played a role, would those additional resistances had the effect in question? Well, okay, they would have added to all the resistance values, not changed T, so that possibly could have caused all the resistance values to be higher in such a way that the slope was too high. Okay? And if the slope was too high, then, because the value for copper is actually lower than what we found, then I can start giving an argument for saying, yeah, that's a reasonable error to associate with any discrepancy. Okay? So you have a measurement argument. You say how much of your experiment can be attributable just to the measurements that you took. This is how everything plays out from the entire experiment, and that includes measurement and any systematic errors. And so you want to argue, based on not only the uncertainties, but also in terms of any percent differences or percent errors in your results. Does that make sense? Because you want to look at the accuracy of your information as well as the precision. And uncertainty calculations only affect the precision, but might give you information a little bit about the accuracy as a side note. Any questions that you can come up with right now? In terms of the error propagation section in the appendix, you're saying, okay, now you're going to be looking at the measurement, the uncertainty associated with the measurements that were taken, using the general form, which should be like equation, C1, okay, applying it to equation 7, and performing some algebra, the following relation can be obtained. Using values from table 6, and selecting, and specifying which values you're using for T, not R, etc. Substituting them into this relation, C3, the uncertainty of this can be obtained and is reported in the discussion section, or wherever you are going to report it. Okay. Questions?
We need to talk about how the uncertainty and the slope was found in origin, or is it enough to just say
And at this point in 2210, you want to be saying, okay, origin is going to be doing a least squares analysis. Okay. By the time you get into 4210, you want to talk about what kind of least squares. Is it a weighted least squares? And there are options that, what option did you pick for doing this? Okay. Is that?
Because, for some resistance values, the uncertainties in those resistance values were not constant. So finding the error and slope and the intercept, you can't do that with what we have in Taylor. Some of the equations we're doing in Taylor.
Right. I mean,
so it's not like I could repeat it without origin.
what do you mean you can't repeat it without origin?
So say I didn't have access to origin and I wanted to write a program that would find the slope, the intercept.
There are
and try to find.
Yeah, and again, that's going to get
uncertainty.
into, what kind of least squares analysis are you going to be doing, weighted or unweighted, and that's a little bit different. Okay, so then and there are documents you can look up,
Right.
and you can actually program Excel to do that for you. You can do the calculations in Excel. Okay, it's tedious, but it can be done. And so you can get a graph in Excel and then do the calculations on a spreadsheet and get values. In my experience, it doesn't change. It won't change the uncertainty of too much from that. Not for this one. Okay, even though this varies, it doesn't vary a whole lot. Okay, but it can in some experiments. Okay, so you got to the point where now you're saying, okay, my value is off by about 10%. Some of it might be attributable to measurement error, but then there's a whole bunch that's not attributable to how do you argue this? Oh, it could be the resistance of the leads, it could be the resistance of the fluid, it could be, going through there. But let's say you say, well, okay, is there anything I can do to decrease that measurement error so that if this is a factor, how could I improve it? We'll leave this. Okay. And so this is where definitely when you get to be a senior in a senior seminar, that's the next step. Okay? Because it's easy to say, get a better DMM. Okay? Let's get a better DMM. We used the Fluke 117s and they were crap. Okay, they're not crap, they're just, they're pretty decent for what can be afforded for labs. Okay, so you do a little research and you find out that, Fluke has another multimeter, and the Fluke multimeter you could get would be the Fluke 87B. Okay, and just for kind of comparison purposes, this is about $400 versus the $200 Fluke 117s.
Is that Amazon prices?
They're not Amazon prices, these are Fluke prices. Okay, so it's about a 2 to 1. Okay, but the reported accuracy for this device is now going to be 0.2% plus 1 count, as opposed to the 0.9% plus 1 count. So if that were the case, then that would affect this. Instead of it being 1.5, this ends up being 0.5 ohms. Instead of this being 1.2, this is 0.4 ohms. So there's a factor of 3 change, reduction, in the uncertainty, or the resistance. Okay? So if you repeat your measurement uncertainty calculation, the only terms that change are these two. And have a significant reduction in the uncertainty associated with the resistance measurement, and they're now all on par. Okay? And when you finish up your measurement uncertainty calculation here, it comes out to be okay, which dropped it down by a factor between 4 and 5. Okay. So this is where you can, when you're not only talking about improvement, in this case, you could take a definite, I've got a manual, I can read this off, and I can tell you what this would be. Let's say you did a measurement with a meter stick, okay, and then you said, oh, well, the uncertainty of that was 0.02 centimeters. I could go to 0.00 using a micrometer, and that you have some other calculation, you could say, oh yeah, if I could have used a micrometer, that would have reduced my uncertainty by a factor of 10, and then my ultimate measurement uncertainty after I did all the calculations dropped by blah, blah, blah percent. Okay? And so you could, so in this fashion, when you're saying not only how much of an impact could it have, you're actually getting a numerical value for the impact that it could have. Okay? Okay? Is that, so you want, not only want to do the error propagation, which is required, but also be thinking about what it could tell you about improvements. When you're doing the error analysis for anything else that's not related to measurement, you want to be thinking about, does it have the impact that you really want it to? Okay. And so if you look at the example that I posted for thermal expansion, then it goes through kind of that same analysis. Okay. Questions? Okay.